Welcome back, chemists. We're now in day 2 notes where we're looking at the reaction rates and the equilibrium, and we'll be focusing now on the equilibrium part of things. We'll also be looking at Le Chatelier, and we'll be predicting the direction of shift for changes in pressure, temperature, concentration, and the addition of a catalyst. So let's first talk about equilibrium. Up until this point, since you've been studying science, you've probably learned that chemical reactions are not reversible. Well, I'm sorry to tell you that, in fact, reactions are reversible. There are some reactions that occur in both directions, and that's what equilibrium is. Equilibrium is whenever you have two opposite reactions occurring at the same rate. So what we would say is that your reactants are colliding and forming products at the same rate in which your products are colliding and forming the reactants. You can identify an equilibrium reaction because now you have this new kind of fancier arrow, and the arrow actually occurs in two directions, so it's like a double-headed arrow. And so that's how you kind of know that the reaction is in equilibrium. One thing that's often confusing for students is they think equilibrium equal. They think equal amounts of reactants and products, and that is just simply not true. Although the rate of the forward reaction, right, as we convert from reactants to products, equals the rate of reverse reaction from products back to reactants, this does not mean that the amounts of both products and reactants are equal. All we're saying is that equilibrium means equal rates. Le Chatelier's principle is a really easy way to describe what is going to occur to a reaction system if we apply a stress. Now, a stress is just something that we add that will change the direction in which the equilibrium is going to progress. So, for example, it changes the rate of one of the reactions. So an example of a stress would be something like a change in concentration, a change in temperature, a change in pressure. All of those will affect the equilibrium. Now, the reaction, we say, is going to shift in a certain direction. And you may be confused by, like, what does that mean to shift? To shift means just to move towards products or move towards reactants, to produce more products or to produce more reactants. That's what we mean by shift. So, for example, if you see in these examples shift right, that just means that we're forming more products as a result of the stress that was added. If you see shift left, that means that we're forming more reactants as a result of the stress that was applied. So let me show you an example. It sounds kind of complicated, but it's not that bad, I promise. So the first stress that we can apply to a system in equilibrium is a change in concentration. So for example, right, if we increase the concentration, the system is said to shift in the direction that will use the substance up, right? So we're going to see the reaction move towards the side to move away from what was added. A decrease in concentration has the opposite effect. The system is going to shift in the direction that will make more of the substance, or it's going to shift towards the side that you removed some of that substance. So here's an example. So we've got the same reaction from the previous slides a few slides ago. But now I'm going to tell you that we're increasing the concentration of SO2. So those square brackets mean increase in concentration, right? We're seeing the up arrow for increase and the square brackets for concentration. So we're increasing the concentration of SO2. And it might be helpful to think about this from a collision theory perspective, because we know when we increase the concentration of something, we've got more reacting particles in a given space. And remember, more reacting particles, they collide more frequently. So guess what? We're going to see that the reaction is going to shift right. And to shift right just means that we're going to take that added SO2, it's going to react with that oxygen, and we're going to form more SO3. So we're going to see more SO3 form, and that's what we mean by shifting right. Here's another example. Let's say we increase the concentration of SO3, right? So notice this is the opposite side, it's the product side. So we add more SO3. The reaction is going to shift to use up that added substance. And again, think about it from the collision theory perspective. If you're adding more SO3, that means the particles are going to collide, and guess what? form more of those reactants. So we're going to say that this change in concentration is going to shift left and form more of those reactants. How about a decrease in concentration? So notice the arrows going down for oxygen. As we previously mentioned, a decrease in concentration is going to indicate to us that the reverse reaction is going to be faster than the forward reaction, right, in terms of collision theory, right, because we've taken some O2 out of the reaction system, so there's not as much O2 to react. So that means that the reaction is going to shift left to make more of the O2 and replenish it. The other thing that's a little tricky for students is you always have to pay attention to the concentrations of pure solids and pure liquids. These have absolutely no effect on the equilibrium. So if I were to say, for example, you're increasing or decreasing the concentration of a solid or liquid, that would be no change or no effect. So here's an example. So let's say I say to you, we're increasing the concentration of NaCl. Well, guess what? No change. It's a solid. So you really got to pay attention to those little symbols that you see in the lower right-hand corner. If we decrease the concentration of sodium, guess what? It's a solid. That's also no change. Let's talk now about changes in temperature. Okay, so when we talk about changes in temperature, we're focusing on whether the reaction is endothermic or exothermic. So we have to look to see what the energy is associated with each of these. So recall, just a quick review. Endothermic reactions can be recognized because they're going to have a positive delta H. You can also recognize an endothermic reaction because you're going to have that energy located on the left-hand side of the arrow, so it's treated as a reactant. For exothermic processes, remember delta H is negative, and you'll be able to identify an exothermic process if your energy is written on the right-hand side of the equation. So here's an example. So it's similar. Notice I've got my energy on the right-hand side of the equation, so it's exothermic. And now what I want to do is treat this energy change as a reactant or a product, just like we did when we changed concentration. So what do I mean by that? Take a look at this. If I increase temperature, what that means is I'm adding heat, right? I'm adding heat, and if I'm adding heat, the reaction is going to shift to use up what was added. So if you guess that this reaction is going to shift left, you're 100% correct. Let's say we decrease temperature. So I'm removing heat. Notice I'm going to where the energy is in the equation, and I'm taking energy out. So if I'm taking energy out, the reaction is going to shift to make more of that energy. So we're going to see that the reaction is going to go right in this case. Let's try this one. So this one is an endothermic reaction, and I know that because I have my energy listed on the left-hand side of the equation. If we increase temperature, let's do the same exact thing. Increasing temperature, we're going to see that in addition of heat on the left-hand side, the reaction is going to shift to use up that added energy, so it's going to shift right. It's going to be more product favored. It's going to form more products. Conversely, if we decrease temperature and remove energy, notice I'm going to the same side. We remove energy, the reaction is going to shift to make more of it, so it's going to go left. So you can see treat temperature changes and concentration changes very similar to what we're seeing. So hopefully that makes it a little bit easier. So just make sure that you find the energy change, write it right inside the equation, and that'll make your life so much easier. Let's talk about changes in pressure. So we can change the pressure of gases only. So if your reaction doesn't have gases in it, then guess what? It's going to have no change. If we see an increase in pressure, it's going to shift towards this side with less moles of gas. So that means you'll have to count how many moles you have in the balanced chemical equation. So for example, we've got the formation of sodium chloride. If we increase pressure, we said the reaction is going to shift to the side with less moles of gas. So notice on the left-hand side, we've got 1 mole of gas for the Cl2, and we've got 0 moles of gas on the right side. So that means that the reaction is going to shift right because of that increase in pressure. Here's another example. When talking about decreases in pressure. A decrease in pressure is going to shift to the side with more moles of gas. So for example, take the same one. If we decrease pressure, that means that the reaction is going to shift left towards the Cl2 because again there's 1 mole of gas versus 0 moles of gas. In this one, notice that we've got 2 moles of gas here and we've got 2 moles of gas there. If we decrease pressure, what do you think is going to happen? If you guessed no change, you would absolutely be right. Great job. One last thing to talk about, addition of a catalyst. The addition of a catalyst increases the rate of a reaction, remember, by lowering that activation energy, but it has no effect on the equilibrium position. So the addition of a catalyst will allow the reaction to reach equilibrium faster, but it doesn't have any effect on the equilibrium position. So that means if you see a catalyst, make sure you write no change. Thanks so much for watching, chemists.